So far we've looked at three types of number patterns: arithmetic, geometric, and Fibonacci. The first pattern we're going to look at are in what are called triangular numbers. Now, triangular numbers are formed when we make patterns that look like triangles. Now, one dot doesn't look like much of a triangle, but if we add two more dots below that and have three dots in all, we can start to see a triangle. And if we continue the pattern, we'll add three dots below that, so we have 6 dots in all, and then 4 dots below that, so that we have 10 dots in all, and then 15 dots, and then 21 dots. You can see that we're forming triangles, and the numbers that we are looking at are the total number of dots in each of the triangles. Now let's think about these numbers that are forming this sequence. It's not an arithmetic sequence because to get from one number to the next, we don't have the same difference. So we don't have a common difference from one number to the next. But if you look at the differences that we do have, you'll notice that the differences, 2, 3, 4, 5, 6, form an arithmetic sequence. So if we'd like to know what the next triangular number is after 21, we simply have to add the next number in the sequence 2, 3, 4, 5, 6, 7 to get the next triangular number. 21 plus 7 is 28. How about this sequence? What comes next? We don't have a picture this time, but we can certainly still look to see if this is an arithmetic sequence, so we can look at common differences, or at least look at differences. And what we'll see is that while we can find differences, we don't have a common difference. But if we look at the second differences, the difference between 5 and 9 and 13, and 13 and 17, we'll see that we have a common difference in our second differences. So to find the number after 45, we're simply going to have to figure out what we're adding to 17. And we'll take this down to the second difference level to add 4 to 17 to see that what we should add to 45 is the 21. So the number after 45 is 66. Now we didn't have a picture to start this one out with, but those numbers actually came from what are called the hexagonal numbers. Hexagonal numbers are formed by starting with one dot and then forming hexagons, that's 6-sided figures with more and more dots, so that we have these nested hexagons. Now suppose we have these shapes, and we have a sequence of numbers that are describing the number of blocks in each of the figures. We'd like to know what the next term in the sequence is, and we'd like to know what the 100th term in the sequence is. So let's start by thinking about the numbers that describe the number of blocks in each figure. We have 4 blocks in the first figure, and then 10 blocks, and then 18 in the third figure, and 28 in the fourth figure. If we look at the differences between these numbers, we don't have a common difference, but there's a pattern in those first differences that we see in the second differences. And we can see that the first differences, 6, 8, 10, do form an arithmetic sequence. So if we continue that pattern and add 2 to 10 to get 12, then we know that we can just add 12 to 28 to get the next number in the sequence, which is 40. Now we also wanted to know what the 100th number was in the sequence. And one way to do that would be to just continue the sequence until we have 100 numbers. But that will take us a long time. So why don't we try to write an nth term formula for this sequence of numbers? Now in order to do that, it's going to be easier to think about the position of each of these figures and what's forming the figures, rather than thinking of the total number of blocks in the figures. So the first figure consists of 1 block by 4 blocks. The second is an array of 2 blocks by 5 blocks. The third one is an array that's 3 blocks by 6 blocks. And the fourth one is an array that's 4 blocks by 7 blocks. Now we're looking for some patterns that relate the position to the products that we see, so that we can write an nth term formula. So the first thing that we notice is that we can match up the position to the first factor in the product. So that means that the first factor in our nth term position has to be the same as the n that represents the position of that particular figure. The second factor has to relate to that position as well. But this isn't a direct relationship, at least not as direct as the first one was. So we have to relate 1 to 4, and 2 to 5, and 3 to 6, and 4 to 7. And what we notice here is that that second factor is 3 more than the position of the figure. So the second factor has to be 3 more than n, or n plus 3. So now we've got our nth term formula, which means it ought to be easy to find the 100th term. The 100th term would be 100 times 100 plus 3, or 10,300. So as you can see, even in these other number patterns, we still may be able to find some of the patterns that we used previously. And if we're clever about looking a little more deeply into what we're seeing geometrically, we might even be able to write some nth term formulas for these patterns.